SwayamPrabha. Digital India. Educated India.
So, once again let us review what we had done in the last class, looking at turbulent flows, which is in equilibrium, and what are the time scales those are involved in turbulent flows. We wanted to estimate by looking at this equation that we called as the turbulence energy budget, which actually looks at the energy associated with the fluctuating component of the velocity. And what you notice is the assembly of this term that originated from this governing equation for fluctuating quantity. And as you can see that these two taken together, when it is multiplied by taken a dot product with V, gave us this term. That is what I have identified there. For example, this term comes from the viscous diffusion term here, right? That is what we get. And this term that comes from here, and there is this term that comes from a combination of this and that. This does not give rise to any contribution when you integrate over the whole volume, that we know. So, then we decided to take a look at a special flow, which we called as a steady homogeneous pure shear flow. Steadiness comes from, if I put the left hand side time derivative equal to 0. Homogeneous will say that all quantities, average quantities, are independent of position. They are same everywhere except the mean flow. Okay? That convects the flow, right? That gives rise to the time rate also. So, that is that, and pure shear flow will tell you that del u I del x j, this are pure constant. And if you do that, then you can see what remains is that this is the term that comes from the mean shear, and this comes from the fluctuating quantity. They ought to be balanced, right. So, that is what we looked at, and we further made some order of magnitude estimate, and we looked at that when we wrote that equilibrium condition. On the left hand side, we saw what was happening was basically the turbulence production term, and because it is in equilibrium, so it must equal to the rate of dissipation. So, that is what we are getting. Now, if we circumvent or try to go beyond this specific case of equilibrium flow and look at general shear flow, then also what we would find that these two quantities are of same order of magnitude. They need not necessarily be exactly identical, and this observation is really the basis for developing all turbulence models. We also note that if we define u cap as a velocity scale, L as some kind of a length scale, then the mean shear would be given like this, and the Reynolds stress that we have is also of the square of the velocity scale itself, and we can plug this information in our equilibrium condition to get this following equation, right. So, what we do get is this, that S I j times S I j, time averaged over a sufficiently long interval, is equal to the product of the mean shear times the Reynolds number. And we have already noted that Reynolds number very large for turbulent flows. So, that would show that on a time average sense, the fluctuating strain rate is significantly higher than the mean strain rate. Okay. We have seen the dimension of Sij is of the order of 1 over T. So, the time scale of dissipation and the time scale associated with the convecting process, they are widely separated. This is the reason that one can perhaps do a Reynolds decomposition. This for the same reason that we can talk about unsteady RANs, because even though the mean may vary slowly, but the frequency of variation is so low compared to the frequency of the fluctuating component, that we can say that they are kind of separated. So, that there is no direct interaction between time average strain rate of fluctuation and the mean flow, provided the Reynolds number is significantly large. So, in a sense you can just simply say it in one sentence that these two events, the mean and fluctuations, they are not tuned to the same frequency band, they belong to a different frequency scales. Okay. Now, if I look at a general shear flow, then we are seeing that the small scale turbulence is independent of the large scale. So, when I am looking at, let us say, turbulent flow over, let us say, aircraft wing, the very fact that I put in a aircraft wing, the eddies are created which are of the size of the dimension of the aircraft wing, right, the chord. So, you could basically look at that, and then what you can see that this small scale eddies do not change under rotation or reflection of the coordinate system. So, basically the small scale is independent of the large scale, and what happens is that the small scales are therefore considered kind of isotropic, because what is happening is you are getting this small scale by successive fracture of the large scale. You have large scale, they break down into smaller scale and so on and so forth. So, when you go to the lowest scale, they have become kind of almost homogeneous isotropic. Okay. This is what is called as a local isotropy assumption of the small scale, and this is used observation is used in large eddy simulation, where you try to derive a model for this small scale, which are anyway not resolved because of your grid. So, you will have to model it. So, you make use of the fact that those scales are isotropic. Okay. So, basically then this is one byproduct of what we have studied looking at equilibrium turbulence. Now, let us get back to this question of relating the mean stress, mean strain rate with the Reynolds stress. What we find that we are again considering an equilibrium condition, and we are talking about a steady state having been reached, and once we have reached that steady state, we get this following equation. So, this is the observation that we would like to make note of, that the Reynolds stress is related to the mean strain when you integrate over the whole domain, is determined by the viscous diffusion term. And the negative sign here implies that the overall effect of V I V j integrated over the whole domain has to be of a similar effect like what you expect out of dissipation. So, basically that is why most of the turbulence model are modeled simply as a sort of a overall dissipative phenomena, right. That is what the sign implies, that it is dissipation. Okay. It also shows that they are not completely uncorrelated, right. What has happened, what we just now talked about, the fluctuating strain rate is uncorrelated to the mean strain rate, but here we are talking about a different thing. We are talking about the correlation between the mean strain rate and the Reynolds stress. So, this is the velocity second moment, right, a fluctuating velocity second moment. So, this is also what is done in most of the algebraic or differential equation based turbulence model, where you eventually try to write out some kind of a algebraic relation or a differential equation which relates the evolution operator of this with the help of the mean strain rate. This is what you do in turbulence models. Now, take a simple example for demonstration purpose. Flow inside this passage where the bottom wall is fixed. So, you do not have any slip here. The top wall is simply slipping by at a constant speed, say u or u bar, while the other two components y and z components are 0. So, basically it is a turbulent coed flow that we are looking at. Now, some of the parameters that defines this flow, of course, is very easy for you to see from the Navier-Stokes equation. The Reynolds number is given by the velocity scale, that is the speed at which the top wall is slipping by. H is the gap between these two walls, and that promotes you to have a exact solution for the laminar flow, because it is a parallel flow. So, you get u is equal to simply u bar z by h. Now, if I want to solve for the turbulent flow, we need to apply, of course, these two boundary conditions. Those two boundary conditions are considered to be time independent, even though the flow is turbulent. And as a consequence, what happens is all the mean quantities are going to be functions of z alone, because we are talking about a parallel flow, right. We have a perfect symmetry in the z direction, and of course, there is no variance in x and y direction. Then if I write down this equation, I will get this term. Okay. You can verify that. You can verify that. This term is of course not there. This term is gone, and this term will not be there. Okay, because of your invariance with respect to x and y direction. Okay. So, what you end up getting from the Rance equation is this shear gradient of the Reynolds stress should be balanced by equal to the streamwise diffusion term. So, it is fairly simple, right. This equation is simple. All you need to do is integrate this equation once. So, on the left hand side I will get V 1 times V 2 is equal to nu times du dz, d 1 dz, or 1 is associated with the x direction at height z minus nu of the same quantity evaluated at the wall. So, we integrated it from 0 to running height z. Okay. So, what happens is we have seen that our equation 24 was what? If you recall, equation 24 was Sij. We had written this, right. This volume integral is equal to minus nu times this, right. So, that is the equation that we have. Of course, there is a factor of 2 missing here. So, what will be the simplest possible turbulence model? That should be given by this, because that is what our previous equation has shown. We just simply looked at it in this form, that 28 tells you that V1, V2 is going to be proportional to d1 dz. So, if we try to do that, we can write it down in this particular fashion, then this will be equal to proportional to this. So, proportionality constant is what we would like to call it as the eddy viscosity. And we have talked about enough to justify why we call it a viscosity, because we saw that V I V j negatively correlates and is proportional to the loss term. So, this also should mimic a loss term. So, that can come about if we position it as a sort of a viscous term. Okay. Now, what is the dimension of eddy viscosity? Is area per unit time, right. So, that is L square T to the minus 1. What about the dimension of this? Dimension of this is 1 upon T, right. This du dz. So, it is 1 upon T. So, then what happens is this must have this kind of a dependence, because if I want to have this dimension as L square T to the power minus 1, then that L square part comes from here, Z square, and T to the power minus 1 comes from this, and they are proportional. So, this proportionality constant I am calling it as a kappa square, and purposely wrote it as square term. So, that the nu T will be positive, whereas the Reynolds stress will be strictly negative. Okay. So, that is the motivation for writing down this expression for nu T, the kinematic the eddy viscosity. So, we have now seen that u prime provides the time scale, the z, the distance from the bottom static wall to any particular height, provides us the length scale. Kappa is a dimensionless quantity, and it has been shown time and again in various other studies that it is a constant due to von Karman taking a value of about 0.4. One can show that. So, basically then what happens is we have a solution for the Reynolds stress. Reynolds stress is simply given by this. Okay. So, what I do is then I substitute this in that governing equation. After integration we have gotten. So, basically V 1 V 2 z is this quantity that is written here, and this is equal to this. So, this is the equation that would basically tell you how the shear is varying with z, isn't it? That is what it is, du 1 dz at different height. So, it is a kind of a quadratic equation. So, you can solve it. If you solve it, you will be able to obtain it, the expression for u 1 z. However, we can also define a velocity scale in a somewhat different way, where we talk about a wall shear that is dimensionally equal to rho times nu times du dz, right. So, that is the definition of this. So, since we are talking about a mean, so that is why this angular bracket has come, and on the left hand side we have written everything in terms of mean quantity. Okay. So, what happens is, if I now divide bring rho on this side. So, tau w by rho gives you a velocity square length scale. So, this is what is called as a frictional velocity. U star is the frictional velocity, which is given in terms of square root of tau wall by rho. So, substitute that expression, and you get this equation, that is the quadratic. Okay. So, we have just introduced the friction velocity, and we have obtained a quadratic for u 1 prime z, and that is your solution, straightforward. And so, this is an expression for du1 dz, right. So, we can integrate it once again to obtain the velocity as a solution. So, where is how is it that this is different from a laminar flow? Where has the thing come about? Well, it has come about because of the presence of the V1 V2, right. V1 V2, those Reynolds stress would be negligible for laminar flow. So, where does this thing come in? In this equation. In this equation, that information comes in through the way we have defined the velocity scale u star, because the tau wall has a built in effect of the turbulence in it. The wall shear itself has information of turbulence being built in there. So, once we can get this velocity scale, then we can get the solution for the velocity profile, right. How do you get this velocity scale? It is very easy. You have that equation, the solution, and apply the boundary condition. The boundary condition is that if I go at the midpoint, it is linearly growing. So, I get this, right. So, I substitute it there and I get this equation. So, what happens is if I choose a Reynolds number, I can solve this equation for u star, right, because everything else is known. Kappa is a constant and Re is known, u bar is known. Only thing that remains unknown here is this u star. So, I can use this equation for u star, the velocity scale. Once I have it, I can go back and obtain the velocity profile. So, that is a very simple application of the ideas of relating the mean strain rate with the Reynolds stress. That is what it is. So, if I now plot the u versus u1 versus z, then this is the way this velocity profile is going to be. So, it is perfectly symmetric about the midpoint. On this side you have one sign of shear, on this side you have the other sign. So, the plate is dragged along like this. So, that is what you are getting. Okay. Okay. So, you get the maximum velocity u bar at z equal to h. So, this is your mean flow solution, what we called as u1 as a function of z, and having obtained that, we can also calculate the Reynolds stress V1 V2 as a function of z, which will be equal to 0 at the wall, is not it, because at the wall you are going to apply no slip condition. So, no fluctuation. So, its time average also has to be 0. Where will it be maximum? It will be maximum somewhere in the center of the passage. Okay. So, that is what we are going to see, that at the center of the gap we are going to get the maximum Reynolds stress. Well, this is just kind of an exercise. You can spend some time looking at it, that what happens to this value of the frictional velocity in the limit Re going to infinity. That is truly a very high Reynolds number solution. You should be able to show that the frictional velocity has this kind of a log dependence on Re. This is at kappa. Okay, this is at kappa. What you could do is you have a laminar flow solution, you have also a turbulent flow solution. So, from those velocity profile you can calculate tau w, and then you try to plot this quantity versus Re, and then you see what you are going to get. So, do take a look at this, and you will be able to see very clearly the distinction between laminar and turbulent flows. Okay, let us now move on to a different approach. See, so far what we have done, we have looked at turbulence as a kind of a time varying quantity, and we looked at it in terms of its time averaged equation, the Rance equation. Now, we have also of course talked about a little bit about large eddy simulation, but not to a great extent. And talking about time averaged quantities, we have made some of the observations, like the role of Reynolds stress is going to be dissipative in a time average sense. But is it true that it happens at all length scales? We are talking about a time averaged value. So, what we would rather like to know is how the turbulence quantities vary as a function of wave number. And this was what was studied in great detail by Kolmogorov by looking at a periodic flow in a box of size L. Okay? So, I have a cube of size L, and I am also going to look at a velocity vector, which I am writing as u as a function of x and t. I can take its Fourier transform. I can take its Fourier transform to get the spectrum. So, u hat as a function of wave number k, and of course, k is a vector. So, you could have all three components. Now, I could get the spectrum, or if I have the spectrum, I could perform a inverse transform to get the velocity field in the physical plane. Right? This what we are doing with the idea of we are looking at a box of size L, and what happens? We are also making an assumption of the flow being perfectly periodic. So, what happens is you are going to get succession of wave numbers in these three directions, which are super harmonic of the fundamental, okay? And the fundamental is given by 2 pi by L. Okay? So, I have it in the I direction, I have it in the j direction, I have it in the k direction, x, y, z directions, and subsequent harmonics will take different values of n1, n2 and n3. So, it is a periodic flow. So, n1 could go from minus infinity to plus infinity. So, can be said about n2 and n3 also. That is what we are looking at. So, once we have defined the velocity field either in the physical plane or in the transform plane, we can invoke what is called as Parseval's equality or identity, which is a very simple observation, that if I look at the kinetic energy per unit volume, that is what I am going to see it in the physical plane, that is half rho times modulus of u as a function of x and t squared. That is exactly the same thing if I would have written down the velocity in the spectral plane. So, that is what we are doing. So, what happens is whether I look at it in the physical plane or the spectral plane, the kinetic energy represented would be the same. Now, if I consider non-periodic flow with arbitrary conditions, then this summation here would be replaced by an integral. I will have to replace Fourier series by Fourier transform. So, that is what we do. And what happens to the box size? Of course, the box size is becoming infinite to that extent that we will take L going to infinity, replace this summation by appropriate integral. Now, what you do is this the appropriate integral would imply that I will have to be talking about an elementary volume in k space, that I am writing it as d cube k. What were the individual fundamental frequencies? That those were 2 pi by L. So, I have in each direction I have 2 pi by L as the interval. So, d cube k is nothing but 2 pi by L. So, then for arbitrary flow I can write the Parseval's equality in this form. So, now you can see we have replaced that summation by integral, and we have written it that L cube we have written it as 2 pi whole cube by d. Okay. So, that is what we have got here. So, this quantity, the kinetic energy per unit volume, is called the kinetic energy density. This is of course a scalar quantity. I am going to do integral over all possible k's, right. So, it is in 3 dimensional k space. So, what I could do is I could do it in a slightly different way. So, for example, if I have this 3 directions, I could write it in let us say Cartesian frame. I could also write it in a spherical polar system. So, if I do it in a spherical polar system, then what happens? I am going to talk about the radius vector of the okay. So, that I could call it let us say as k bar, and an elementary volume in spherical polar system would be what? Would be a sort of a spherical shell of width, I will call it as dk. So, what happens to the elementary volume in this case? What we are going to do is, see, there we are talking about 3 variables in the x, y and z direction. So, what we are doing here, here also we are doing the same thing, k bar, and then of course, we will talk about this angle theta and this angle phi, right. That is what we do. However, what we are talking about, let us say we perform the integral in theta and phi direction, and then it becomes what?